We've been using magnets for 2,600 years. Electric motors, MRIs, hard drives, fridge magnets holding up takeout menus. And yet, if you ask a physicist what magnetism really is, they might echo Feynman. I can't explain it without saying it just is. That's not laziness. That's the edge of physics. This video is about why that answer is honest. It starts with Einstein, not magnets. How does relativity explain magnetism? And why does it still leave a hole? Here's how. Ancient Greeks found weird rocks that attracted iron. They called them lodestones. They had no idea why. They just knew it was strange. 2,600 years later, we built civilization on them. Generators, speakers, the magnetic stripe on your credit card. We got really good at using magnetism. We wrote equations. Maxwell in the 1860s unified electricity and magnetism into one theory. 4 equations. Beautiful, complete. For the 19th century, those equations said moving charges create magnetic fields. That's the classical explanation. Current in a wire deflects a compass needle. Done, but here's the problem. That's a description, not an explanation. It tells you what happens, not why. Why does a moving charge create this weird sideways force? What is the magnetic field actually made of? Maxwell's equations are silent on that. They just work. Like a microwave, you push the button, food gets hot. Don't ask what the microwaves are doing in there. So physicists kept digging. And the answer they found is genuinely surprising. Magnetism isn't a separate force. It's electricity seen from a moving perspective. This is where Einstein comes in. Special relativity, 1905. He showed that space and time are not fixed. They stretch and squeeze depending on how fast you move. One consequence is length contraction. Objects shrink along their direction of motion, not metaphorically. Actually, now take a wire, a simple copper wire. Inside, you've got positive metal ions sitting still, and free electrons drifting along. When no current flows, the electrons are just hanging out. The wire is neutral, equal positive and negative charge. No electric field outside. Now run a current. Electrons start moving. They're drifting at maybe a millimeter per second. Slow, but relativistic effects care about speed, not slowness. Here's the trick. From the perspective of a stationary test charge outside the wire, those moving electrons experience length contraction. Their spacing shrinks. The positive ions are stationary, so their spacing stays the same. Suddenly, from the test charge's frame, there are more electrons packed into the same length of wire than positive ions. The wire becomes negatively charged, and a stationary test charge feels an electric force. It gets attracted or repelled. That force is what we call magnetism. The magnetic field is just a component of the electric field in a different reference frame. When you see a compass needle swing near a wire, you're watching relativity in action. In the wire's frame, it's a magnetic force. It's not 2 separate things. It's one thing viewed from different angles. Magnetism is electricity plus motion. But, and this is a huge but, this only explains electromagnets. Wires with current. What about a permanent magnet? A fridge magnet just sits there. No current. No moving charges. No obvious length contraction. Yet it sticks. It lifts paper clips. It defies gravity for decades without a battery. Where's the motion now? Enter the electron. Every electron behaves like a tiny bar magnet. It has a north and south pole. This comes from a property called spin. Spin is intrinsic angular momentum. The electron isn't actually spinning like a little ball. It can't be. If it were, its surface would have to move faster than light. Spin is a purely quantum thing. No classical analog. It just is. And because the electron has charge, this spin gives it a magnetic moment, a tiny magnetic field. In most materials, these tiny magnets point in random directions. They cancel out. No net magnetism. But in a few materials like iron, the electrons can align. Their spins all point the same way. The tiny fields add up. You get a macroscopic magnet. That's a permanent magnet. Spins aligned. No current required. Now the mystery deepens. Why does the electron have spin? Quantum mechanics describes it mathematically. Dirac's equation from 1928 predicted spin naturally. It fell out of combining quantum mechanics and special relativity. Beautiful, but it doesn't explain why. It just says spin is a fundamental property, like mass, like charge. The electron has spin because that's what an electron is. Asking why is like asking why a circle is round. It's a definition, not an answer. Feynman again. In his QED lectures, he said the magnetic field is a relativistic effect of the electric field. But then he added, why the particle has spin, I cannot explain without saying it just is. That's the most honest statement in physics. The guy who helped build quantum electrodynamics, the most precise theory ever invented, shrugs at the fundamental question. And QED is precise. It describes magnetism as the exchange of virtual photons between charged particles. You can calculate the electron's magnetic moment to 12 decimal places. Theory matches experiment. It's the best tested prediction in science. But QED takes spin as input. It doesn't generate spin. It says, given that the electron has this weird angular momentum, here's exactly how it interacts. The origin is still a brute fact. Then there's the monopole problem. Electric charges come in isolated positives and negatives. You can have a lone proton, a lone electron. But magnets always come with both poles. Cut a bar magnet in half. You get two smaller bar magnets, each with a north and south. Cut again. Same result. You can slice down to individual electrons, and each one is a dipole. Two poles, always paired. No isolated north, no isolated south, no magnetic monopole. Why not? The equations of electromagnetism are almost symmetric. Maxwell's equations would look cleaner with monopoles, more elegant. Some grand unified theories predict they should exist. The early universe should have made them. We've searched. Cosmic rays, particle accelerators, moon rocks, nothing, not one. If monopoles exist, they're absurdly rare, or they don't exist at all. And we have no idea why nature chose to forbid them. It's an empirical fact, not a theoretical necessity. The universe just said no, so here we are. 2,600 years after Thales rubbed lodestone and freaked out his friends, we have a relativistic explanation that turns magnetism into a perspective trick. We have quantum electrodynamics that calculates magnetic interactions to inhuman precision. We have spin, which gives us permanent magnets and MRI machines and data storage. And we have zero understanding of why spin exists, or why monopoles don't. This is not a failure of physics. It's a feature. Physics doesn't answer ultimate why questions. It builds models. The models make predictions. The predictions work. The fridge magnet sticks, the motor spins, the hard drive stores your files. That's success. The fact that the deepest layer is just it is so isn't ignorance. It's the boundary of the model. The map isn't the territory. And at the edge of the map, there's a note. Here be dragons, or more accurately, here be unexplained fundamental constants and postulated intrinsic properties. So next time you look at a fridge magnet, you're staring at the edge of human knowledge. A thing we use without thinking. Holding up a shopping list. Powered by a property we cannot explain. Sitting on a device that cools food using thermodynamics we do understand mostly. The magnet doesn't care. It just sticks.